Okay, so let's take a look at an example. It's practice quiz 8, 1b. It says use the Laplace transform to solve the initial value problem. So we're given here y double prime minus 4y prime plus 4y equals t cubed e to the 2t. And we have that y of 0 is 0 and y prime of 0 is 1. So we're going to use the Laplace transform to solve this. So we're going to take the Laplace on both sides, and we're going to be using these theorems here. So in particular, theorem 17, the n equals 1 and 2 case. So theorem 17 for n equals 1 case, it would say the Laplace of y prime equals s, Laplace of y minus y0, and the n equals 2 case for theorem 17, Laplace of y double prime equals s squared Laplace of y minus s y of 0 minus y prime of 0. We'll be using theorem 18 also, which says if the Laplace of f is big F of s, then the Laplace of e times f is big F of s minus a. And theorem 14, Laplace of t to the n is n factorial over s to the n plus 1. Okay, so let's take the Laplace on both sides, step 1. So doing that we get this, and now the Laplace transform is a linear operator. It means I can take this in here, distribute in. So doing that we get then, so we get this. The negative 4 can come outside the plus, and so can the 4, because it's a linear operator. Okay, then we're going to apply theorem 17 part 2 to this guy, so this one, and theorem 17 part 1 to this one. So applying it to this one first, we get then, okay, so again, Laplace of y double prime would be s squared Laplace y minus s y0 minus y prime of 0 by part 2 of theorem 17 here. And applying part 1 then to Laplace of y prime, let me write it here. So doing that we get, okay, so we get then in place of this we can write s Laplace y minus y0. Okay, then we still have plus 4 Laplace y, let me write it here, equals this. So we'll get this will be our guy now, after we took the Laplace on both sides. Now let's work on the Laplace of t cubed e to the 2t. Let's first find Laplace of t cubed. Let me write it over here. So the Laplace of t cubed, so put n would be 3 here. So it'll be 3 factorial over s to the 3 plus 1. So 3 factorial 6, so it's going to be 6 over s to the 4th. Okay, so it'll be 6 over s to the 4th. We're going to call this big F of s, because we're going to now apply theorem 18, because we have t cubed e to the 2t. So let me write this guy over here and apply theorem 18 to it. Okay, so we're looking at the Laplace of t cubed e to 2t. I'm going to switch around the e to 2t and t cubed so I can match it up with theorem 18 better over here. Okay, so I have it written as Laplace of e to the 2t t cubed. So here in theorem 18, the a in our case would be 2. So the a is 2 here. So according to theorem 18 then, it's going to be big F of s minus a. So it's going to be big F of s minus 2. And this is my big F here. So it's 6 over s to the 4th. So we're going to replace the s with s to the 4th. So it looks like going to be 6 over s minus 2 to the 4th. Let me write that here. Okay, so we get then the Laplace of e to the 2t t cubed is 6 over s minus 2 to the 4th. So that's going to go over here. And also, in place of the y0, it's 0. In place of the y prime, it's 1. So let's make these substitutions. So let's replace this, and let's replace all the y's and y primes. So let me write down here the result. Okay, so we get this. So again, the y prime is 0 is 0, so that'll be gone, that term. This is 1, so it's going to be s squared Laplace of y minus 1 for this part here. Then minus 4 times s Laplace of y, y0 is 0, so just be then plus 4 Laplace y equals Laplace of t cubed e to the 2t, but that is equal to 6 over s minus 2 to the 4th. Let's factor out the Ly's here and here. So doing that, we get then okay, so I factored out Laplace y here and here, so there'll be an s squared left there, minus 4s plus 4 Laplace y, then still minus 1 equals 6 over s minus 2 to the 4th. Okay, so I'm out of space here, so let me erase a few things and we'll keep going. Okay, so summarizing, we got the here. Now notice the s squared minus 4s plus 4 will factor as s minus 2 squared. And let's take this minus 1 across over here. So doing that, we get then okay, so the s squared minus 4s plus 4 factors as s minus 2 squared, Laplace y, then I took this 1 across over here. Now I want to solve for the Laplace of y, so let's multiply both sides by 1 over s minus 2 squared. So solving for Laplace of y, we get then okay, so solving for Laplace of y, so multiplying both sides by 1 over s minus 2 squared, you'd add 2 to that, be 6 then, and be 1 over s minus 2 squared here. Now we want to solve for y, so we're going to take the Laplace inverse on both sides to solve for y. So doing that, we get then okay, so taking Laplace inverse on both sides. So Laplace inverse of Laplace is going to be y here, and the Laplace inverse is also a linear operator, so it's going to go in like this. So then simplifying this, we get then okay, so we have our y then equals, so the 6 can pull outside, so it'll be 6 Laplace inverse of 1 over s minus 2 to the 6th plus Laplace inverse of 1 over s minus 2 squared. So if we can find these Laplace inverses, then we'll have our answer. So let's figure out how we can find these Laplace inverses. So let's make some observations. Okay, so I've written theorem 18 here again, and written theorem 14. So theorem 14, Laplace of t to the n is n factorial over s to the n plus 1, and theorem 18 here. So let's figure out from theorem 14 and 18 what the Laplace of e to the at t to the n would be. So according to theorem 18, it's just going to be the Laplace of t to the n, which is here, evaluated at s minus a. So just replace the s here with s minus a. So you can see that these guys look like that. So in particular then, we can take Laplace inverse on both sides here. So doing that, we get so taking Laplace inverse on both sides here, then it would say that e to the at t to the n is the inverse Laplace of this guy here. I can pull out that n factorial outside. So let me do that. So I pull out the n factorial from here. Then I can divide by n factorial. So doing that, we get then okay, so we'll then have the Laplace inverse of 1 over s minus a to the n plus 1 is e to the at t to the n over n factorial. We could then apply that to these two guys here. Okay, so I'm out of space, so let me erase a few things and we'll keep going. Okay, summarizing, we have it here. I'm writing the 6 as 5 plus 1 and writing a 2 as 1 plus 1, so I can apply the formula we just derived over here. So in the first one, looks like the n is going to be 5 for that one. Okay, so the first one, the n's 5, the second one, the n's 1. So applying this guy with n being 5. So it looks like, and actually the a would be 2 here also, so a is 2 in both of these. So it looks like the first one would be e to the 2t, t to the n, so 5 over 5 factorial. And the second one would be e to the 2t, t over 1 factorial. So let me write the answers here. So to get this then, so using this formula, so again, a is 2, n is 5, so it'll be e to the 2t, t to the 5 over 5 factorial for that one. And a is 2 again, n is 1 here, so it'll be e to the 2t, t over 1 factorial. 1 factorial is 1. 5 factorial is 5 times, 4 times, 3 times, 2 times 1. So simplifying this, we get then okay, so again, 5 factorial is 5 times 4 times 3 times 2. So the 3 and the 2, cross off the 6 up here. 1 factorial is 1. I put the t first just to make it look nicer. So our final answer then will be, t to the 5th e to the 2t over 20 plus t e to the 2t. So this should be the solution to the initial value problem at the beginning. So I'll let you check that if you wanted to. Okay, so we're done, so let's leave it there.